Right now we're going to take one last look at Gibbs Free Energy and even more information that we can get from that. And we're going to start by looking at a situation that seems like it doesn't make sense. If we look at the equation for water evaporating, turning from a liquid to a gas, and we measure the standard Gibbs Free Energy for that, we get a positive number, which tells us that this is a non-spontaneous process. But we know that water evaporates, so this doesn't seem to make sense. But what we need to go back and keep in mind is that this standard Gibbs Free Energy applies to standard conditions. In this case, when there's a pressure of 1 atmosphere. These are not normal conditions. Typically, in the open atmosphere, there's only 1 atmosphere of everything total, all the gases. So there's a very, very small percentage of that would be water vapor at any one given time. So these standard conditions are not typical of ordinary conditions. We didn't pick standard conditions because we commonly encounter them. We just picked them because it was an easy set of conditions that we could compare between different laboratories. So the standard Gibbs Free Energy that we can find tabulated in our textbook is not always that helpful for trying to determine if a reaction is spontaneous under a given set of ordinary conditions. Fortunately, we have an equation to get around that, which is this last equation down here. Delta G generally, under any set of conditions, is given by the standard Gibbs Free Energy change plus R, which is just a constant, times temperature, times the natural log of Q. And if we remember, Q is equal to products over reactants. Previously, we used Q in the equilibrium chapter, where we would compare it to our equilibrium constant, K, and we had 3 scenarios. Q could be equal to K, it could be larger than K, or it could be smaller than K. When Q is equal to K, we said we were actually at equilibrium. So my reaction was just going to stay exactly where it was. My reaction is always trying to get to equilibrium. When Q is larger than K, that means we have too many products, so the reaction is going to go in the reverse direction in order to reach equilibrium. When Q is smaller than K, that means I have too many reactants, so my reaction is going to go in the forward direction in order to reach equilibrium. We also thought about it on a number line. If you think about K, if Q is too big, it's going to go in reverse. If Q is too small, it's going to go forward. This is just to remind us where we saw Q previously. Now we see we're going to use it in a fairly similar way. We're going to calculate Q and plug it into this equation up here, and we're going to look at delta G. If delta G is negative, that's going to be a spontaneous reaction. Delta G is positive, that means it's going to be a non-spontaneous reaction in the forward direction, which means instead it's going to go in the reverse direction in order to reach equilibrium. Now, of course, you might say, well, if we already knew how to do that in equilibrium, why are we doing it again in a different way? And the answer is delta G not only tells us if the reaction is spontaneous or non-spontaneous, it also gives us an actual number that tells us how much energy we can get out of a reaction. So if I wanted to figure out which way the reaction is going and how much energy I could take advantage of and get out of that reaction, delta G is going to be a more useful quantity. That's why we're going to look at that instead of just comparing Q to K. So good news, we can get delta G for any set of conditions, figure out if a reaction is spontaneous or not. We can also get out one last piece of information. Let's consider that under a specific set of conditions, we reach equilibrium. In that case, delta G here is going to be 0 because we've reached equilibrium. Now, if we're not under standard conditions, then the standard delta G will not be 0 because we're saying we're at equilibrium under some non-standard conditions. So just delta G is 0, but this standard Gibbs free energy is not 0. And then we're still going to have the plus RT times natural log, but since we're at equilibrium, instead of Q, we can call this K. So if we rearrange this very slightly, we see that the standard Gibbs free energy change is equal to negative RT times the natural log of our equilibrium constant, K. So what this means is, just like we were able to look at K previously and figure out if my reaction was overall reactant or product favored, now the standard Gibbs free energy is going to give us the exact same information. So if we go back, we look at this relationship. Q is now equal to K. We're at equilibrium, so delta G is equal to 0. We have this expression right here. We can figure out what sign of delta G is going to tell us about reactant and product favored. So if we have a very small K, if K is less than 1, then when we take the natural log of that, that's going to give us a negative number. A negative times this negative will give us a positive. So when you have a positive delta G, your reaction is reactant favored, right? Because a small K meant it's reactant favored, and a small K leads to a positive delta G. On the other hand, when you have a large equilibrium constant, we know that means it's product favored. If we plug in a large number here, that's going to give us a positive number. A negative times a positive is going to give us a negative delta G. So a negative delta G implies that my reaction is product favored. On the rare occasion that K is equal to 1, so we have roughly equal reactants and products, the natural log of 1 is going to be 0, so delta G under standard conditions would be 0 here. So under the rare circumstance that your K is equal to 1, under standard conditions you should be at equilibrium. So just to recap between what regular delta G tell us and this standard delta G. Delta G, similar to Q, tell you if the reaction is going to go forward or reverse at a particular moment under a very specific set of conditions. Whereas K, or delta G naught, that standard Gibbs free energy, tells you that once the reaction reaches equilibrium, am I going to have more reactants or products? So Q and regular delta T are really telling you what's going to happen right now. Right now, are we going to go forward or are we going to go in reverse? Whereas K and the standard Gibbs free energy really just tell you what will you have once you finally reach equilibrium. So this is like the end goal. What will you have left? And Q and delta G just tell you right now, are you going to go forward or are you going to go in reverse? So we can do a lot of things with this new information. First of all, we can look at just delta G under any conditions and figure out if my reaction is going to go in the forward or the reverse direction. We can also look at the standard delta G, the standard Gibbs free energy change, and figure out once my reaction reaches equilibrium, is it going to be reactant or product favored? We can also quantitatively, if we have this standard Gibbs free energy change, actually figure out my equilibrium constant or vice versa. So we can do a lot of conceptual things and a lot of mathematical things with this. So of course, let's look at an example. Consider the following reaction. And here we're given a reaction and a standard Gibbs free energy change. First of all, is this reaction product favored or reactant favored? So here's where we have to remember that relationship we just discussed, that this standard Gibbs free energy change is directly related to K. So by looking at whether this is a positive or negative number, I can figure out if it's reactant or product favored. So I sort of like to associate these. A positive delta G we normally thought of as being non-spontaneous, so it likes to go backwards. That means this is going to be reactant favored. A negative we typically think about being spontaneous. It likes to go forward, so that's going to be a product favored. So negative is product, positive is reactant. So we go back to our example. We have standard delta G is equal to negative 71.2. Negative G means likes to move forward, so that's going to be a product favored reaction. All right, nice conceptual. Now let's do something mathematical. Calculate the equilibrium constant at 25 degrees Celsius. So if we think about the two new equations we've learned, only one of them has K in it, and that's that standard Gibbs free energy change is equal to negative RT times the natural log of K. So all we really need to do now is plug in and solve. So we have our Gibbs free energy change, that's this guy right here, so negative 71.2 kilojoules per mole is equal to negative R is just a constant 8.314 joules per mole times Kelvin. Now we used kilojoules, so I need to turn this into kilojoules, so I'm just going to divide that by 1,000. 8.314 over 1,000. We'll turn those joules into kilojoules per mole Kelvin. I now need temperature. Now that was in Celsius, so my temperature, I have to add the Celsius to 273 to get my Kelvin there. So that's going to give me 298 Kelvin. And then I have natural log of K. So the first thing I'm going to do are just multiply the number together, and then I'm going to divide them over to the other side. We can see since I have a negative on each side, these are going to cancel and become positives. And my units are also going to cancel. My kelvins will cancel. And when I divide these over, my kilojoules and moles will cancel. So if I divide these over to the other side, I find that I get 28.7 is equal to the natural log of K. So I just 71.2 divided by this piece, divided by this piece. Now, I can't leave it here. I want K, not the natural log of K. So to get rid of natural log, we use E. So these will cancel. K is equal to E to the power of 28.7. So we're going to get a really big number, which is going to be 3.02 times 10 to the 12. And now we can see, oh, K is a really, really big number. This definitely is product favored. So this agrees with the answer we got just by looking at how big delta G is, whether it was a positive or a negative number. Beautiful. One more thing we can do. So here we just determined, generally speaking, is it reactant or product favored? What's the value of K? Now let's look under some specific conditions. So instead of those standard conditions, just some specific conditions. Determine if the reaction is spontaneous in the forward or reverse direction under these conditions. When it's asking about various conditions, not standard conditions, that's when we're going to use our delta G is equal to the standard delta G plus RT natural log of Q. So if we look at our equation here, in this case Q, remember we just do products over reactants, is going to be NO2 squared, because I got that 2 there, over NO squared times O2. So that's my expression for Q. So really simple, all I need to do here is plug in my numbers. So I'm looking for delta G, because that's what tells me if it's spontaneous or not. I'm given my standard Gibbs free energy, that's negative 71.2 kilojoules per mole. R, of course, is 8.314, but once again, I need to put it in kilojoules, so I'm just going to divide that guy by 1,000, so my units match per mole Kelvin. 25 degrees Celsius, we saw that that's 298 K. I'm kind of running out of room here, but this next piece is also multiplied. It just connects right there, just running out of space. So now we plug in our information for Q. So NO2 we see is 2 atmospheres. So we have 2 squared on top. And then we have NO, which is 0.0100 squared. And we have O2, which is also 0.0100. That guy's not squared because I only had 1 oxygen. So I just need to, I'm taking the natural log of Q. So I just plug in Q, take the natural log of that, and then I'm going to, well, that whole piece goes in here. I just ran out of space, but that natural log is just multiplied by R and T. So I plug this whole guy into my calculator. I don't even have to break this up. I can just directly type in negative 71.2 plus 8.314 divided by 1,000 times 298 times the natural log of this whole fraction. And if I do that, my delta G reaction is equal to negative 33.5 kilojoules per mole. And all I really need to look at is the fact that it's negative. That tells me that this is a spontaneous reaction, and it's going to go into the forward direction. If I had gotten a positive delta G, that would mean it was a non-spontaneous, and it would want to go in the reverse direction. An additional piece of information, now I know I can use 33.5 kilojoules per mole from this reaction under these conditions. So that again is why this is a little more convenient than just looking at Q and K. I don't only figure out if it's going to move in the forward or reverse direction. I also figure out exactly how much energy that reaction is going to give me.